this talk is going to be justified, in view of the title of the conference. This is basically a joint work with my PhD student Mohit and Panteleimon Stanica. This is already published work. This work was published by IEEE Transactions on Information Theory this year only. So I'd like to, the way I plan to, okay, so just a minute, and just slides are not moving. So let me see what is the problem. There appears to be some problem. Yeah, they are moving now. So here is the outline of my talk. So I'll begin with the notations and some definitions. It's going to be with the mathematical talk. And then I'll talk about what are additive and multiplicative characters. Then I'll also talk about differential uniformity and its generalization, recent generalization, what is known as the C differential uniformity, where C basically is nothing but some element of the finite field. And then I'll talk about boomerang uniformity, and then I'll conclude my talk by listing some open research problems. So that's the basic idea of the talk, basic outline of the talk. So now coming to the notations and definitions. So as usual, we always denote by a finite field having q elements by fq, where q is some prime power. So there is a unique field having p to the power n element, and that uniqueness is up to isomorphism. And if you look at the non-zero elements of the finite field, they form a multiplicative cyclic group, and its generator normally known as primitive element of the finite field. So fq star basically denotes the multiplicative cyclic group of non-zero elements of the finite field. So if you take any function from the finite field to itself, any function, then it turns out that it can always be uniquely expressed as a univariate polynomial of degree at most q minus 1. So that can be done by using Lagrange interpolation or otherwise. So this is not very difficult to prove this fact, and those who are interested can look at the book by Liddell and Niederreiter on finite fields, which was published by Cambridge University. So the functions over finite fields are quite interesting because you can express them as a polynomial. So it doesn't happen, when you are dealing with arbitrary fields. But if you are over a finite field, then the functions are suddenly quite interesting because you can express them as a polynomial. And therefore, essentially, functions over finite field or polynomials over finite field, they are same notions. There is no difference in view of this. So either we talk about polynomials over finite fields or functions over finite field, they are essentially same. Now coming to a very special class of polynomials over finite field, they are known as generally permutation polynomials, and they are very, very useful not only in cryptography but also in coding theory and other combinatorial objects. So what is a permutation polynomial? It's basically a map from finite field to itself, which is 1, 1 and onto. So there is a bijection between fq to fq. So such a polynomial or such a function is known as permutation polynomial, and they are very important object when it comes to block ciphers actually. So I don't know, there is again some problem in movement. Yeah. So now some examples of the permutation polynomial. So if you look at the polynomial 4x to the power 5 plus 3, where the coefficients are coming from the finite field f7. So f7 is basically 0, 1, 2, 3, 4, 5 up to 6. So if you look at the image of 0 under this map, fx is basically 3. You plug here 0, then you get 3. Image of 1 is going to be 4 plus 3, and 4 plus 3 in the finite field f7 is nothing but 0. Similarly, image of 2 is 5, image of 3 is 2. Likewise, image of 4, 5, 6 is 4, 1, 6. So if you see that, it's basically permutation from f7 to f7. So it's a permutation polynomial because it permutes the elements of the finite field f7. So this is one example of a permutation polynomial. We should give an example of a polynomial which is not permutation. So if you look at the polynomial gx, 2x squared plus 3 over the same field f7, coefficients are from f7, and there if you look at this table, so 0, yeah, is there any question?
No, sir.
Okay. So if you look at 0, 0 goes to 3, 1 goes to 5, and 2 goes to 4, 3 goes to 0, 4 goes to 0. So if you look at, the element 3 and element 4, that goes to 0. Both of them, are being mapped to 0. So it's not 1-1 map, right? So it's not permutation polynomial. So permutation polynomial has to be 1-1 as well as onto. And also it is not onto because if you look at 1, so 1 has no pre-image under this map G. So it is neither 1-1 nor onto, and therefore it is not a permutation polynomial. So not every polynomial is permutation. So it's very interesting problem in mathematics and cryptography, how to construct polynomials. The simplest question is, can we classify all the monomials over a finite field that are permutation polynomials? So the answer is yes. So if you take a monomial x to the power d over a finite field fq, then it is going to be permutation polynomial if and only if the GCD of d and q minus 1 is 1. So the monomials have been completely characterized, which monomials are going to be permutation polynomials. But then there are other questions like what about binomials, what about trinomials, pentanomials? So those are still open problems, and people are trying to classify, when a binomial is going to be a permutation polynomial. Of course, there are specific results, specific binomials that have been proved to be permutation polynomials, but we do not have any general criteria where we can say that, oh, this is a binomial and this is going to be permutation polynomial because it satisfies these following conditions and so on. So those are open questions, and they can be taken up by the research community. So now I'll introduce what is called additive and multiplicative characters. These I am going to introduce because we have to study the cryptographic properties of certain permutation polynomials. So these things would be required at that time. So I'm just introducing in the beginning itself. So a canonical additive character is nothing but it's a homomorphism from finite field fq to the field of complex numbers C, which is defined as chi1 x equal to exponential of 2 pi I trace of x divided by p. So it's a here you are taking fq as additive group, and then you are defining this homomorphism. Then this homomorphism is known as additive character, where C is the field of complex number and TR denotes basically the absolute trace map, which is given by trace of x equal to x, x to the power p, x to the power p squared, and so on, x to the power p to the power n minus 1. So this is how you define additive character. We can also define multiplicative character. So the multiplicative character is again a homomorphism from multiplicative group. So fq star is a multiplicative group. If you remove 0, it is in a multiplicative group, and it's again a homomorphism from fq star to C, and this is how it is being defined: psi k g to the power L is nothing but exponential of 2 pi I KL divided by Q minus 1. So here G to the power L, they basically, for L equal to 0 to Q minus 2, that they represents the elements of FQ star. You remember G was the generator of FQ star. In the beginning, I denoted generator of FQ star by G. So all the elements of G are going to be G to the power 0, which is 1, and G squared, G cube, and up to G to the power Q minus 2. So you are basically defining the map psi k for each element of FQ star, and this is how you are defining. So this is called multiplicative character. Now they can be correlated, and we can define something called Gauss sum. So here is relation between this Gauss sum actually sort of combines both additive as well as multiplicative characters. So the Gauss sum is defined as summation psi x and chi x. Chi x is additive character, psi of x is multiplicative character, where x is running across the non-zero elements of the finite. So we may not use Gauss sum in the subsequent slides, but we'll use what is known as Weil sum. So here is the definition of Weil sum. So chi is an additive character, and fx is any polynomial in fqx, and then the Weil sum of the function f is normally denoted by sf, and this is nothing but you, instead of evaluating the sum at the element of